Alright, welcome back. Now is time for the next lecture. Variables, assignments, math, and strings. We'll only get through some of this today, don't worry. Here are my goals, and let's get right on into it. Let's talk about things that can go wrong, because I tried my hardest to write correct programs, but last lecture, but that's never something that is always going to happen. No matter how many years you've been programming, you're always going to make mistakes and you're always going to do things wrong. So you're going to run into a bunch of different kinds of errors that can happen. And I want to make sure you know the lingo so that you know how to Google for them and just how to solve them in general. So the first kind is probably the most common, a compile time error. So this is what happens, especially when you're starting out, when you're speaking C++, it's like a language, of course, and the compiler doesn't know what you're talking about because you spelled something wrong, or you forgot a semicolon, or you did something weird like that. Okay? You forgot the main function. Who knows? So, the compiler won't even try to translate your program is the main thing. So, a common compile time error is like, I don't know, int instead of int equals 42. Something like that. And then, of course, this is the error. Okay. That is the idea. And I might as well just show you an example of this. So let's go to our handy dandy terminal. So I'm in my CSCI 40 folder. Got nothing there other than last lecture. Well, let me make, ooh, that was a fun key combination. Let me make a brand new folder called lecture 1, or lecture 2, sorry. So the way you do that is you say make dir folder name makes a new folder called folder name. Whee. Put that up here. So that's that. So I'm about to make a lecture 2 folder. Hit enter. There it is. It's beautiful. Oops. Alright, so now I'm inside of it. There's nothing there. Let's put something there. Vim compile time error.cpp. Okay, so let's pretend I won't even include IOStream because we won't get to printing. We won't need it. So I'm going to say int x equals 42. And actually my Vim will tell me, yes, it'll kind of compile it for me in a sense, but here's my mommy terminal, here's my baby terminal, and now I will go into the same folder so that I can show you the code at the same time as me compiling it. So in order to compile, so G++, standard equals C++17, the name of the program, and then you can also say -o optionally, and then the name that you want it to be compiled into. Hit enter, and then it'll say, dude, what are you talking about? What is int? And it'll be nice and tell you what line it's on, and that is your standard compile time error. Okay? And, I mean, you can do more. Optionally, you can forget the semicolon. That's another compile time error. And now it'll say it expected like a comma or a semicolon before return, and that's helpful enough, I think. Sometimes you'll get really weird compiler errors and you'll have to ask questions about them or Google them, but at least most of the time in this class I think you'll get nice looking ones like the ones we've just seen. Okay, runtime errors are a different breed. So a runtime error happens when your program's running. So you got past the compiler. The compiler wasn't smart enough to find this bug or this error. And one of the most common runtime errors, as you're doing mathematical operations, is called divide by 0. So let me show you that. So the compiler isn't smart enough to know that you're going to divide by 0 in this case, so it lets you compile the program. And I'll show you why that's a good idea. So vim divide by 0 .cpp. Now, alright, include IOStream, using namespace standard, And remember what these are for. This is for cout and cin, and also endl. And this is for, so that I don't have to say standard cout, so that I don't have to say standard cin. Okay. Back to the main function. And, alright, we're ready. So, I'm going to ask the user for something. Please enter a divisor. And then, we're going to perform an operation. These parentheses aren't technically necessary, but I think they help. We're going to say 42 divided by the number that the user types in. Let's call it n. So, let's make space for it. Int n. Make space in memory for n. And then we'll get n from the user with cin. Oops. There we go. And then we'll output to the user 42 divided by n. So when this program runs, it's quite possible that you're not going to type 0. So obviously the compiler should let this through because we want to trust our users, right? Well, we probably should never do that, but that's okay. A lot of the times, like, you'll be calling with a number other than 0. There's many other ints in the world. So let's compile this. Divide by 0. Output as divide by 0 without any suffix. Hit enter. Compiles, so it got past the compiler, and now I have this divide by 0 program that I can go and run. And notice that compile time error never made its program because it never compiled. Please enter a divisor. I guess I didn't need that new line. I'll show you the difference. Here I'm typing the new line, which means it's going to ask me for the number on the next line. Say 2. And it'll divide 42 by 2. Hey, it's 21, sure. If you don't ask for the new line, like I did last lecture, then it'll put the prompt on the same line as it asks the user for information. So now it's saying, please enter a divisor, and it'll let you enter it on the same line, which I think is a bit nicer. So now we'll say 2 again, 21, I don't know. What else is 42 divisible by 3? 6, yeah? 14. We'll get into integer division in a second, but now I'm going to say 0. And this is definitely something that I did not print out in my program. So this is the operating system complaining. It's like a floating point exception. Those are some scary words all right next to each other. Core dumped. What in the world is this? Well, we divided by 0, and that's what you're going to see. This is called a runtime error. The program was running for a second, but something so bad happened that we could not recover from this issue, which was division by 0. Okay. Logic error is kind of in between in severity. Like, it's not as bad as a runtime error, but it's insidious. That's the right word. A logic error is also known as a bug, and the way that logic errors work are the program works, it runs, it compiles, it runs, nothing happens. It doesn't stop itself prematurely. Like, it is ready to do whatever, and it does it, but it just doesn't do the right thing. And here's an example. Let's say we had int x equals 42 again, and then we make a new variable called int, I don't know, x plus 1. And we set that equal to x plus 2. I think you see where I'm going with this. So the issue is, well, anybody who's ever going to use this variable, including ourselves, are going to expect a 1 to be there instead of a 2. You're going to expect 43 instead of 44. So your program's going to run. It's going to calculate whatever you asked it to calculate. But it's not going to give you the right answer, and that's what a logic error is. Okay? So I hope you see the difference between these three things, and yeah, that is all I want to say about that for now. So now I want to get into what I will call a fancy demo. So this is a bunch of stuff that we're going to learn in the first half of this class, and I want to, in essence, speak C++ to you right now. I want to speak it in its full form, mostly, and I want you to pretend that you're much younger than you are right now, and you are still in that stage of brain development where you can learn a native language just by listening to it. So I want to try this out because I think it will be helpful. back in undergrad, I took a Latin class from Dr. Chapman at Fresno State. She's wonderful. Please take her if you go there. And what she did one day is she took a page of Latin out of our textbook and just started reading it to us. We didn't know enough Latin to understand it, but it helped us to understand like the syntax of the language, the way it flows. So I think that I can do the same thing here, and it will be helpful for you. So please let us sit back and watch me make something that is a bit fancier than usual. And if at any point you get overwhelmed, totally skip this. This is not something I'll test you on right now at all. This is just for you to see where we're going and to hear some terms for the first time so that they're not too scary when I say them later. Okay? So what we're going to make is we're going to model this thing called a counter. This little counting machine. I don't know, I've heard that it's like used a lot in athletics, right? Like you're counting as many times somebody's jump roping to like score them. I don't know. Count how many laps you've done on the track. Something like that. And so we're going to model this with a brand new type. We're going to call it counter. And it's going to have, it's going to be really fancy. We'll call it counter. And it'll have some data associated with it. So it'll have like its own little variables. And it'll be called count. And then we'll have some functions associated with that. Don't worry that I've said this word and you don't understand what it means. Just roll with it right now. All right. We'll have an initialization, we'll have a reset function to make our count 0, because we always want our counter to be reset when we use it. And then I'll make an increment function that adds 1 to, that's a C and these are parentheses, to the current count that we're working with right now. So we kind of want it to start with 0, and then when we call increment, it'll make it 1, for example. Okay? That is the idea with our counter. So let's make it. Vim counter.cpp. And again, I'm not going to test you on any of this right now. It's just for your education, to hear some words that I'll say later. So this is the idea. I want to make a brand new type for myself called counter. I want to make a new variable of that type. Just like I'm making an int, for example. And then I'll reset it to make its count 0. I'll say c.reset, because this function belongs to C. Counter's count to 0. And then I'll start pressing the button. All right? And I will model the pressing the button part with the inc function for increment. So if I press c.inc 3 times, what do you think should happen when I output the counter's current count? These are all the things that belong to C by virtue of being of the type counter. So what do you think should be output right here? I think you'd be right to think that, all right, this line made it 0, this line made it 1, this line made it 2, this line made it 3. So in theory, this should print out current count 3. And that's exactly what will happen. So I'm going to make a brand new type called counter. It'll be a class. That's how you make a new type. Class counter, sorry. It's hard to say something and type something else. All these things will be visible to the user. That's what public means. The user can see all the things below, but we won't get into what that means right now. So public, we're going to have a int count variable inside of this counter. We're going to have a function called reset. It won't return anything, it'll just do something, so it's a void function. And we'll get into what that means later in this class, don't you worry. And then we'll have an inc function that changes the count to 1 more. Okay, so I'm going to implement these now. I'll say reset will be set the count to 0 whenever that's called. And I'll say inc that will add 1 to the count whenever that's called. It's like pressing the button. All right. Don't worry about any of this. Don't worry. And so now I've made this type. I made this new variable called counter of that type. I've reset it I've added 1 to the count, I've added 2 to the count, added 3 to the count, then I've printed out the count. Okay? So I'm going to compile and run this for you. I'll put it over here maybe. Now you can see it all. Current count 3. Isn't that nice? You can keep all these things together logically. That's really helpful, I would think. So now, let me reset it one more time. And then call inc twice. What do you think's going to happen when I print out the current count down here? Take your best guess. And yes, it's 2. Okay. So that is the quick example of this thing called a class and all the functions that we made inside of it. Void's a weird word, and we'll talk about that later, but this is kind of where we're going in the class, and it'll take us a few weeks to get here. Okay. So hopefully you stayed for the whole thing. Thank you for watching. I think it will be helpful for you to have seen those things. So now let's talk about variables. Alright, so we made a few already. We made x all the time. It's my favorite variable name, obviously. So a variable is just something with a name that can hold a value that you can use later. Like, you don't have to type the whole big thing anymore. So there are some naming rules for variables. So a variable has to start with either an underscore, a lowercase letter, or a capital letter. And after that, you can start using numbers as well. All right, so here is a valid name for a variable name. So you can call it, I don't know, underscore var 2b. That's a valid name. Here's an invalid name, $x. Okay? So just understand the difference. The compiler will complain, so it's not a huge deal. And it's common for people to write many words at a time, and I've done this in the file names for the variables. And oops. In order to separate the words, because you can't use spaces in your variable names, people just start capitalizing it when it's a new word. So this is called camel case because it looks like the capital letters are the humps of the camel's back. Okay? So this is like one big long variable name, and to make it easy to read, we capitalize it when a new word starts. So that's one way to make a variable. And there's another class of people that prefer to use underscore in between words. That's all. Okay, so those are variable names and common styles of doing it. Now if we want to make a variable, what really happens under the hood? We've been using this, but we've been doing it in a kind of a contrived way. All right, I've been saving you from any of the possible errors. So to declare a variable, you have to specify its type. So this right here, let's see, where do I want to put it? If I say int x equals 42, this is what's known as both a declaration and an initialization. And initialization. Okay, so what does that mean? Try to make a better T for you. There we go. All you need to declare a variable is to specify its type. So this is the declaration part of that. Okay, so we say, I want a variable called x. Make space for it in memory for me, please. So this is just a declaration. And it's not initialized. So whereas this line will make a box in memory called x and have it hold 42, this line will make a box in memory and have it hold what? What in the world will it hold when it's not initialized just yet? Will it hold a special value, like 0? Well, the answer is, if you're not looking at the left side, it holds complete garbage. It holds whatever was in memory at the time that you made this variable, that you asked C++ to make it for you. So in essence, it's going to be a random value. You might get a special, nice-looking random value, but you cannot depend on that. All right? So let me show you that. Initialize vars.cpp. So I'm going to use all the types we know. I'm just going to make a few of them. and show you the issue at hand. Int x, char c, double d. That's probably enough. Alright, now let me print them out for you. Cout x colon, and then the actual value of x. And then we'll do the same for c. Oops. Oops. Oh, sorry, and then this was supposed to be d. There we go. So I'm going to print them all out, and they are all uninitialized. It's hard to spell. Uninitialized. Okay. Let's compile and run this. No, I didn't save it, did I? Oh gosh, was I making these in the wrong folder? It's quite possible. Oh no, it's there. There it goes. Alright, /uninitialized bars. That's going to print out whatever it thinks x, c, and d are right now. They're uninitialized. They have no value. So it looks like x is this, c is a character with an that is a question mark in a diamond, and d just so happens to be a nice value. It looks like 0. If I rerun this program, they can change. Do you see that? Ooh, the character became the character S this time. How fun. Now it's the period, and this changed to that. So you have no guarantee over what these are, even if you rerun the program. Oops. And this is called undefined behavior. It'll work differently on different computers. Okay? So we don't like that. So please always initialize your variables. And there are 2 ways that you can do it. The first way is the least error prone. You can declare and initialize at the same time. Or, especially if you're using C and you have to do this, you have to make space for it and then give it a value down here, maybe a little bit later. Okay, then you can say like x equals 42. Or you could do, alternatively, like int x cin x to give it a value. But the idea is, no matter what, you better not have used x in between right here. That is a no-no. You should only ever use your variable after it's been initialized. Okay? Because then you know it has a value and it won't be weird. That's all. And now let's talk about this equals. So when you say equals, either if you're declaring and initializing or you're just giving it a value later, the equals is called the assignment statement. A equals B is called an assignment statement. With a semicolon, of course. Call it an assignment statement, so it gives a value, and takes whatever B was, puts it into A. So that's what, that is probably something we should write. It takes B and puts it into A, whatever B is. And B can be arbitrarily complicated, like 2 plus 3 plus blah blah blah. Doesn't matter. Just whatever this right-hand side is, it's going to put it into the variable called A. Okay? And that's why the name equal sign was a horrible decision. Equality in math means it has a value, this variable has a value, and it's never changing. In C++, we're not that lucky. Variable values can change. So x right now can be 42, but later it can be 43. All right? So watch out for that. And so now let's get into some fun little assignment statements that really tell you the nature of how this stuff is working. Another thing that I should say is the right-hand side of the assignment statement gets executed first. And then whatever it comes up with, whatever the value it evaluates to, that's what gets put in the variable on the left-hand side. LHS for left-hand side. Okay, so that's why you want to read an assignment statement from right to left. If you say something like x equals 42 plus 1, first it's going to make 43 out of that and then put it into x. It's got to do a little bit of work. That's the idea. Okay? So now let me show you some weird looking assignment statements. Okay, so here's my int x equals 42. What do you think is going to happen if I say x equals x plus 1? You might remember from the counter example, but this is interesting. Let's find out. Assignment. This just so happens to add 1 to x. So that's why it's always important to read from right to left. The right-hand side evaluates first to an int value, and then that is put into x. It's okay to talk about yourself because it won't happen at the same time. The right side happens first. Weird, huh? And then there's another one, x plus plus. What do you think that one does? It also adds 1, so it's equivalent. Which is pretty funny. Oops, that needs to go in there. So now you know the reason why this is called C++. There was a language called C, and C++ was built on top of that as like a better version with cooler things. And so now you know why it's called C++. Alright, there's one more with this kind of style. X plus equals 1 is also another kind of shorthand for adding a certain number. And so this one only adds 1. This one can add whatever you want. X plus equals 5, for example. Maybe I'll keep it like that. Okay, and so you can run and compile these, and they'll do what you expect. Okie dokie. Moving on to expressions, literals, values, operators. So these are some words. You will read about them in your textbook. I just want you to see them. So a value is a basic element of a type. And so remember when I drew that cloud of ints? This is the int type. I drew all the basic members of that type. The values, the things where C++ doesn't have to do any extra work. These are what ints really are. Their final value, 42, 0, -5, 720, why not? ... What's not in here are things like 2 plus 2, because this requires work to be done. Okay? The compiler has to send this, make a machine code instruction to add numbers, and the CPU has to do work to add these numbers in order to make the 4 that is the final value that can be stored later. Okay? Because you don't want to have to do any extra work after you've made your int and you've stored it somewhere. You just want to get it out and not have to do anything extra. Okay? So that is the idea. And yeah, so a value or a literal is just one of those things. For an int, it's a number. For a character, it's just a single character. We've mostly been working with literals at this point. We've done a few operations like this, like plus and times. An expression, on the other hand, technically includes values as a special case, but mostly when I say expression, I'm talking about something with more than just values. Okay? That is the idea. So an expression would be something like 2 plus 3 times x divided by 7 ... minus 1, because why not? And so the idea is this will be evaluated by C++ into a final int, which is, I have no idea, but let's pretend that x was whatever it needed to be to make this 42. All right? So this is the value, and this is just an expression. All right? That's the differentiation there. All right, how are we doing? Let's check the time. Okay. Division is the next thing I want to talk about. It's a type of arithmetic, and it can throw you on a spin if you don't know about this thing called integer division. So I showed you division without any decimals so far. Showed you division on ints. So the division operator in C++ for both doubles and ints is the slash, but it operates differently on ints than it does on doubles. So let's see what that means. Let me include some. Let me cheat a little bit and copy some of this boilerplate for myself. There we go. Okay. So integer division. Let's get some numbers from the user and divide them. Int x and y. So you can use commas to declare multiple variables at once. Okay, so right now, after this line gets executed, this is what happens in memory. It just made brand new space for both x and y that are ints, but right now, of course, their values are uninitialized. So let's give them values. Let's say x equals 42, comma y equals 43, or we can get them from the user. We can say cout, enter dividend is the first. Let's just say x and y, because I can't remember the difference between dividend and divisor. I think the divisor is the one below. It's the one that does the dividing, but don't quote me on that. So now we have an x. So now at this point, after these two lines get executed, x will have been filled in, right? So if we typed 42, x will now have 42. If we type 43, we need to give the user a place to do that. If we want to initialize y with that. So now we'll enter y as well. And now we'll also have 43 if the user types in 43, for example. Okay, so this is just a program. It's very simple. It takes two numbers, and let's have it output x divided by y. Now we can actually output x. X space the division sign space y colon space x divided by y. You'll see how this looks, but take a guess. That'll be useful for us. Yeah. There. Alright, let's run the program. X can be 4, y can be 2, then I'll print 4/2:2. Alright, so it did the dividing right here. and it printed 2 for us. Okay, now let me type 1, 2, and so divide 1 by 2. Take your best guess as to what this needs to be. The answer is actually 0, and that might be very confusing for you. So in an int, when it's doing integer division, it's just going to squish things down. It's going to drop the decimal places. It won't round. Ints can only hold whole numbers, and so we had 0.5, and it converted that to just 0. Okay? So for example, 0.5 gets converted to the integer 0. So that's what happens with integer division. And so same for like 5 halves. The answer is 2, because 2.5, get all the decimals dropped, not rounded. Just 2. So that's integer division for you. Alright, if you weren't confused enough, now let's talk about double division. So when you want to divide 2 numbers using the slash operation, you want to have the decimals saved, so you want to make a double type. Well, let me show you where that can go wrong. Let's see here. What I'd like to do is, let's just do it down here. Cout 1.0 divided by 2.0. Okay? Or actually, let me do it like this. Double D equals 1 divided by 2. Then I'll output D. Okay, so at the very end of this program, we should see 1/2 printed out after D colon. Oh gosh, I still have to enter X and Y every time. Maybe I should make a new file. Sorry. No, we're taking our stuff elsewhere. There. Copy all this, put it there. Just because I didn't want to do that extra typing. So we'll call this double division. Okay. And when I run this, what? It's assigning to something that can have decimal places, but it's giving me back. It's giving me back 0. What? So this is the trick. This is the tricky case. Double division, or the division operator itself, is the one that cares about the types. Okay? So it doesn't matter what you're assigning to. It doesn't matter that we're assigning the result of division to a double variable that can hold the decimal places. If both sides of the slash are ints, this will perform integer division no matter what. Alright, so the solution is to make at least one side a double. So now, can't redefine D, but I'll just change it to be 1.0 divided by 2. So now we actually get those decimals saved because one of the sides of the slash was a double, and so it knew, now I'm going to do double division, and the result of this operation will produce a double. All right. Just in case you see this, let me put this one here, and just say this as an aside. Double is also known as a floating point type. And floating point means just the fact that it can hold a decimal point. It can hold things that are not just whole numbers. Okay. So, ooh, I don't know what I just did, but sorry. I think I just selected everything in a weird way. There we are. So this won't work, of course. You can't just type 0.0 if you're using a variable. What if we want to do this? Int x equals 1, int y equals 2. See out. And then we say d equals x over y. Well, because x and y are ints, we'll never get 1/2 the right way, you know? And this, just to prove it to you, will print 0 again. No fun. Well, the way to convert an x or a y, to convert a variable, or just an arbitrary expression, from one type to another, use static underscore cast. I know that looks scary, but just roll with me for a second. Static cast, type you want, parenthesis, variable or expression, close parenthesis. So this will convert this expression, usually a variable, into the type that you care about. All right? So in order to convert y, for example, into a double from the int that it was, I will say static underscore cast into a double, because that's the type I want, of y. That's how we'll read that. All right, so now we've guaranteed that one side of this slash becomes a double, particularly this side. We just force that y into a double. And now it'll print the 0.5. Okay? Dun dun dun. And then finally, one last thing that I want to talk about for doubles is how to print them using fixed and set precision. So this can be a little weird to talk about, or just confusing that you're giving things to see out that aren't things that get printed. Let's talk about printing doubles. Okay, so how do I want to say this? Let me just give you some examples first. Let me see out 1.0. See out. All right, let's just make a double. Double d2 equals 1.0. Yeah? See out d2. And we'll say what we're doing. It is a curious thing that when we print it, d2 becomes 1. Even though we know it's a double, it has this decimal point, but it doesn't show when it doesn't need to show it. Okay? We can force it to show. That's the idea. Let me this is a new section, printing doubles. Okay? So, to force the decimal place to be shown, pass standard fixed to cout. And of course, you can always pass just fixed by itself because you're using namespace standard. So this is weird. I'll say cout fixed. Nothing gets printed as a result of this. And that can be very confusing. This is just a special modifier that when cout sees fixed, it knows to start printing the decimal place for doubles. Okay. And so now if we print d2 again after this, oops, dun 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 dun. Now, watch what happens. It starts printing the decimal place. And 6 zeros, that's the default. Okay. To force the number of decimal places to be what you want, you can add set precision. with a certain number. So if we wanted to round our doubles when we print them to 2 decimal places, we'll say set precision 2. This rounds the output, but does not change any variables. And I'll show you what I mean. So let's say set precision 2, and set precision lives in the standard library, so it's standard : : it lives in the IO manip for manipulation. IO stands for input output, manip stands for manipulation, so it lives in the IO manip library. So now IOStream has a friend. Okay. So now we'll say to cout, and again this doesn't print anything, it just like controls the way cout does things. Set precision 2. Alright? For all future doubles, this is what we're telling cout. Print after rounding to 2 decimal places. Okay. Now if we print D2 another time, we'll print 1.00. Alright? Dun dun dun. And now just to prove that set precision isn't changing the variable, let me make double D3 equals 1.5555. And I'll print out D3. There. It will of course round it to 1.56, but I can then go around and change set precision again. Like that. Oops. Like that. And let me make it have 5 levels. 5 decimal places. And so you see it never really changed D3, it just changed the way it printed it. That's what set precision does. Okay? That is, that was a lot of information about doubles, but now you know. Okay, let's check time. Alright, these will be like the last 3 things. So let's talk about characters now. We've talked about numbers enough. So characters in the ASCII table. Oh gosh. Well, I'll have to restart that. That's okay. So characters in the ASCII table. At the end of the day, remember that all your programs, all your data, everything gets turned into 0s and 1s. So everything is really just a number. It just gets converted before the terminal shows us stuff. Alright, so characters in particular are a special kind of number. And it just sees that, alright, I have the character for A, it's a certain number, I'll look it up in a table, and when the terminal goes to print out an A, it knows that it needs to go look up what pixels to fill in that make the A symbol. Okay? That's kind of the idea. And so, how did people know? Well, actually, let me show you. It's more fun. It's more fun to discover it. Okay. Sure, I can see out. Well, here's my character. Chars C equals. Actually, let's just have it be whatever the user types. Chars C, ask the user, type a character. Then get it from the user. Okay, so now we have a C. It was whatever the user typed. So then we can say, cout C, that'll print the character itself. Really, with a space, really is the number. And then we'll convert. You know how to do that now. Hey, we're going to use static cast into an int of C, and then it'll try and make it an int. It'll get the number out of it and print it as that number. So this is called chars.cpp. Type of character. All right, what's our favorite character? I don't know. A. A is really the number 65. B is really the number 66. Lowercase a, 97. Lowercase b, 98. $, it's 36. Now you might be asking, who decided this? Well, it's just a bunch of people in a room one day decided the order of the characters. That's how this works. So, yeah, just capital A. It's actually 65, weirdly enough. Oh, and the numbers, the character 0, that'll throw you. That's weird. The character for 0 is the number 48. That's disgusting, right? It's the number 0. Character for 0 is the number 48. And so the order of these things is, one of the orders is called ASCII, and so that's the one that our terminal is using. So let's go here. ASCII table. Dun, dun, dun. Well, maybe I should just look up ASCII and then it'll give me Wikipedia. Oh, there it is. Beautiful. I think you want to see it in English. Here's the table. It's got some weird stuff at the start. These are decimal numbers. We'll look at this lighter blue column. And yeah, here are the printable characters. A space is decimal number 32. There's that character for 0. There's A. And the lowercase letters come after some symbols. That's how this world works. That's your ASCII encoding of characters. How fun. So that's that. And then finally, these last two slides for today, let's talk about strings. So strings are just a bunch of characters at once, but because they're made up of individual characters, we should be able to extract them and modify them. Okay? So we can use this fancy notation. We can say we have a string s, looks like this in memory, and say .at I to get the ith index of a string s, we say. Okay. Well, let me copy all this, and I'll just make a new file inside of him. It'll save me some time. Again, let's have the user enter not a character, but a word. Because when you get a string from CN, stops reading, or CN stops reading into a string once it sees white space. So if you were to have typed at this point, hello world, S would only be hello. It stops after it sees the space. Okay, that's all. So CN gets a word at a time. We'll show you ways to do this, to get a whole line. So now let's start printing this kind of stuff. You can pick out the individual characters of a string. And so this is how this works. Let me now pretend that our program got here. It said type a word, we typed a word. And let's pretend we typed the word hello. Or you know what, let's pretend we typed the word the. I'll do it up here. At that point, in memory, we made S, which has some things inside of it. It has all the characters for the word the. It has the T, it has the H, it has the E, and we can access those. If we wanted the T, we could say we wanted S, go inside of S and get the 0th index. If we wanted H, we say the 1st, the 1th index, the 2th index, because second isn't really the same, because now it's the 3rd is under the 2. And so this is something that is confusing when you start out. Indices start at 0 for most things in this class. So for strings, if you want the first character, you have to say s.at 0. Okay? And that'll get you the T. So let me prove that to you. We'll say cout first character. and then we'll say s.at. That's the at function on the string s. It gets a certain index into the character, into the string, and outputs the character at that index. We'll do the same for the second and the third. Oh, sorry. So this is weird. The first character is 0, the second character is 1, the third character is 2, and I think that email means that my office hours might have to change. Sorry about that. That is that, and now it'll print out these things. Yeah, that's all I want to do right now, actually. Whee! So let's compile and run its strings this time. /strings, type a word, the, first character T, second character H, third character E. And you can also use @ to edit. So you can say s.at 0 equals the character A always. So now it'll print out, even if I type in the, it'll change the first character to A, which is weird. Alright, and then finally, let's make an example where we capitalize a lowercase string. So we'll take the first character, that is s.at 0, and make it capital. So in order to do that, we need to figure out how much we need to do. So how far away is lowercase a, 97, from capital A, 65? Let's do some quick math. Actually, we don't have to worry yet. Don't think too much, because these are really numbers. And so let me show you a trick. So all we have to do is add. That's what we do. If we're going to add, or actually really subtract. And it really is that, because these characters are numbers from the character, the distance between lowercase a and, or the other way around, capital A and lowercase a. Okay? Because they're all in order after that. Capital B comes after capital A in the order. Lowercase a comes after, or sorry, lowercase b comes after lowercase a in the order. So as long as we just take away as many as we need to get down to the capital letters, we'll have done the thing correctly. Okay. So let me compile this one, or comment out that one, and now let's capitalize the string. And this won't work if the user types the first character that's not a capital, or that's not a lowercase letter. We can fix that later. Alright, so we need to do something like this. s.at 0, so the first character needs to change to be whatever it was plus the offset in between. Now this is going to look weird because we're adding characters and subtracting characters, plus the offset between lowercase a and capital A. And I think I had it the wrong way. This should be a negative number. Now let's see if this works. Dun dun dun. I might be off by 1. Let's run this, type the, and wow, it capitalized it. And we can say lowercase hello, and we'll make it capital H. As soon as you start giving non-lowercase letters, it's going to do weird things because it always offsets by the same amount, but this is just going through the table, offsetting the letter to go from the lowercase to the capitals. So that's a fun, slightly complicated example. And that's where I want to leave you today. The next time we meet, we will talk about the sizes of types. Well, in a lecture at least. We'll be meeting for lab, of course. And yeah, we'll learn about binary and cool stuff like that. But that is enough for the lectures for this week, so thank you for getting through it with me. Thanks for putting up with me, and I'll see you in your lab.